December 19th, 1943. A cold, clear morning over the English Channel. German Luftwaffe pilot Oberleutnant Hans Meyer sits in the cockpit of his Focke-Wulf 190, scanning the horizon for the expected formation of American B-17 bombers. He is 26 years old, a veteran with 41 confirmed kills, holder of the Iron Cross First Class. He knows this sky. He knows how to fight here. Below him, the anti-aircraft batteries open fire. Black puffs of flak bloom in the winter air, the usual pattern. Predictable. Survivable. Meyer has flown through this dozens of times. You watch the bursts, you read the pattern, you find the gaps, standard defensive fire, dangerous only if you are careless or unlucky. Then something changes. A shell explodes 30 meters from his aircraft, not where he was, where he is going. Another detonates directly in his flight path before he reaches it. A third erupts precisely at his altitude as he attempts to climb. In 7 seconds, his wingman's aircraft disintegrates in a ball of fire. Meyer pulls into a violent dive, his mind racing. No one fires this accurately. No one predicts movement this precisely. This is not possible. He will make it back to base that day, but 14 of his squadron mates will not. And in the debriefing, when his commander asks what happened, Meyer will say something that sounds absurd. They were not aiming at us. The shells knew where we were. This is the story of how one engineer's impossible invention changed the mathematics of air defense, how a device so secret that workers building it did not know what it did eliminated hundreds of Luftwaffe pilots in a matter of weeks, and how the Germans, despite capturing examples early, despite their own advanced technology, could never replicate what the Americans had created. Because sometimes the most devastating weapon is not the one that destroys the most, but the one that makes the enemy's skill suddenly completely irrelevant. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The problem was simple to state and impossible to solve. Anti-aircraft fire in 1941 was essentially the same as it had been in World War I. A shell was fired into the air, it climbed to a predetermined altitude set by a mechanical time fuse, and it exploded. If an enemy aircraft happened to be close enough when it exploded, the shrapnel might damage or destroy it. If not, the shell was wasted. The statistics were brutal. In the early years of World War II, it took an average of 2,500 anti-aircraft shells to bring down a single German aircraft over Britain. 2,500 shells for one kill. The mathematics were unsustainable. British factories were producing shells as fast as possible. American factories were ramping up production, and it was never enough. The Luftwaffe could afford to lose one aircraft for every 2,500 shells. The Allies could not afford to fire 2,500 shells for every kill. The core problem was timing. A time fuse relied on perfect calculation, perfect weather prediction, perfect intelligence about enemy altitude and speed. In practice, enemy pilots changed altitude constantly. Wind affected shell trajectories, temperature variations altered fuse timing. By the time a shell reached the altitude where it was supposed to explode, the target aircraft had moved, climbed, descended, turned. The British had experimented with radar-directed anti-aircraft guns. These improved accuracy significantly, but the fundamental problem remained. The shell still exploded at a preset time and altitude. It was still a matter of prediction and luck. What was needed was something that had never existed, a shell that could sense when it was near an enemy aircraft and detonate itself automatically. A proximity fuse. The concept was not new. Engineers had imagined such a device for decades. The problem was making it work. You needed a sensor small enough to fit inside an artillery shell, rugged enough to survive being fired from a gun, experiencing accelerations of 20,000 times the force of gravity, reliable enough to work after spinning at hundreds of revolutions per second, sensitive enough to detect an aircraft at useful range, and smart enough not to detonate prematurely from clouds, rain, birds, or the ground. Every attempt had failed. The British had tried photoelectric cells, 2, fragile. The Germans had explored acoustic sensors, too unreliable. The Americans had experimented with various mechanical solutions. None survived the shock of firing. By mid-1941, the proximity fuse was considered a theoretical possibility with no practical solution. A nice idea that belonged in science fiction, not on a battlefield. Then a man named Merle Tuve decided that impossible was not an acceptable answer. Merle Anthony Tuve was 41 years old in 1941, a physicist, director of the Department of Terrestrial Magnetism at the Carnegie Institution in Washington. He was not a military man. He had spent his career studying the ionosphere, cosmic rays, the fundamental structure of matter. He was a scientist, methodical, precise, more comfortable with equations than with explosives. But Tuve understood something that many military engineers did not. The proximity fuse was not primarily a mechanical problem or an explosives problem. It was an electronics problem. And electronics, specifically radio electronics, had advanced dramatically in the previous decade. The technology existed. It just had to be miniaturized, ruggedized, and made foolproof. In June 1941, Tuve assembled a team at the Carnegie Institution's Section T, a division created specifically to develop the proximity fuse. His team included physicists, electrical engineers, mechanical designers, and specialists in explosives. None of them had ever designed a weapon before. That, Tuve believed, was an advantage. They would not be limited by assumptions about what was possible. The basic design concept was elegant. A miniature radio transmitter inside the shell would broadcast a continuous signal. When the shell approached a large metal object, an aircraft, the signal would reflect back. A receiver in the shell would detect this reflected signal, amplify it, and when the strength reached a certain threshold, meaning the aircraft was close enough, trigger the detonation. On paper, it was simple. In practice, every component presented seemingly insurmountable challenges. The radio tubes needed to be miniature, roughly the size of a rifle cartridge. They needed to survive 20,000 Gs of acceleration. They needed to operate reliably at high altitude, in extreme cold, after spinning violently. Standard vacuum tubes shattered instantly under such conditions. Glass could not handle the stress. Filaments broke. Seals failed. Tuve's team spent 3 months developing a new type of vacuum tube. They experimented with different glass formulations, different mounting systems, different ways of anchoring the internal elements. They fired prototypes from test guns again and again, examining the wreckage, identifying failure points, redesigning. By September 1941, they had a tube that survived firing half the time. That was not good enough. The power supply presented another nightmare. The fuse needed electricity to operate the radio transmitter and receiver. A battery was too heavy, too unreliable in cold, too likely to fail under acceleration. The solution was a miniature generator powered by a small propeller on the nose of the shell. As the shell flew through the air, the propeller would spin, driving a tiny dynamo, producing electricity. This sounds simple. It was fiendishly difficult. The propeller had to spin freely immediately after firing, despite just having experienced forces that would crush most mechanical devices. The generator had to produce stable power despite the shell spinning and tumbling. The electrical connections had to remain intact despite vibration that would shake apart most assemblies. The entire mechanism had to fit in a space smaller than a soup can. By December 1941, Tuve's team had working prototypes of individual components. The tubes functioned. The generator produced power. The radio circuit could detect reflections. But when they assembled a complete fuse and fired it, it failed. Every time. The components worked individually, but not together. The vibration from the generator interfered with the radio circuit. The radio signal triggered false detections from the shell's own spin. The detonator fired prematurely, or not at all. The United States entered the war on December 7th, 1941. Suddenly, the project was no longer theoretical. It was urgent. The Navy needed proximity fuses for anti-aircraft defense of ships. The Army needed them for anti-aircraft defense of ground installations. The British needed them desperately for defense of cities against air raids. Tuve's team was given unlimited resources, unlimited priority, and a deadline that seemed impossible, working prototypes by June 1942, 6 months to solve problems that had defeated engineers for 2 decades. Tuve divided the team into specialized groups. One group worked exclusively on the vacuum tubes, testing new designs, new materials, new manufacturing techniques. Another focused on the power supply, refining the propeller generator, developing backup systems. A third group worked on the radio circuit, improving sensitivity, reducing false triggers. A fourth group handled integration, figuring out how to make all the pieces work together inside a shell that would experience forces no electronic device had ever been designed to withstand. They worked around the clock. The Carnegie Institution became a factory, a laboratory, and a testing ground. They fired hundreds of test shells from a naval proving ground in Dahlgren, Virginia. Each failure was analyzed in microscopic detail. Each success was documented and replicated. Slowly, painfully, the components became more reliable. The breakthrough came in April 1942. An engineer named Harry Diamond, working on the radio circuit, realized that the false triggers were caused by the shell's own rotation, creating a Doppler shift in the reflected signal. The radio receiver was detecting the shell's own signal bouncing off the ground or clouds distorted by motion and mistaking it for an aircraft. Diamond developed a filter circuit that could distinguish between reflections from stationary objects and reflections from moving metal targets. It was a simple modification, a handful of additional components, but it transformed the reliability of the system. Suddenly, the fuses stopped triggering prematurely. They began to work as designed. By May 1942, Tuve's team had a functional prototype. They assembled 10 complete fuses, loaded them into 5-inch anti-aircraft shells, and conducted a live fire test at Dahlgren. The target was a radio-controlled drone aircraft flying at 8,000 feet, typical altitude for a bombing run. The anti-aircraft gun crew was not told about the special fuses. They simply aimed and fired using standard procedures. The first shell exploded 40 feet from the drone, too far for a kill, but close enough to cause damage if it had been a real aircraft. The second shell exploded 20 feet away. The third detonated within lethal range. The drone was destroyed. 3 shots, 1 kill. Compared to the usual 2,500 shells per kill, it was a revolution. But this was a controlled test. Perfect weather, a cooperative target flying straight and level, a single drone. Real combat would be far more difficult. Enemy aircraft would be maneuvering, diving, climbing, flying in formation. Weather would be unpredictable. Shells would be fired in volleys, creating electromagnetic interference. The fuses would have to work not once, but thousands of times in every condition without failure. Tuve knew they had proven the concept. Now they had to prove it could be manufactured in massive quantities, used by ordinary sailors and soldiers, and remain secret from the enemy. Because if the Germans learned about the proximity fuse, if they captured one and reverse-engineered it, the advantage would disappear. Worse, they might develop countermeasures, ways to jam or deceive the fuses. Security became obsessive. Workers manufacturing components were not told what they were building. The vacuum tubes were disguised to look like standard components. Blueprints were compartmentalized so that no single person saw the complete design, except for Tuve's core team. Even the name was chosen to be deliberately misleading. Officially, it was called the VT fuse, variable time fuse, a name that revealed nothing about its actual function. Production began in July 1942. The Western Electric Company, maker of telephone equipment, was chosen as the primary manufacturer. Western Electric had experience with delicate electronics, with mass production, and with quality control. They converted an entire factory to proximity fuse production, training workers to handle components that were far more fragile than anything they had built before. The manufacturing tolerances were extraordinary. vacuum tubes that would fail if a filament was off-center by 1/10 of a millimeter, generator coils that required hand-winding with microscopic precision, detonator assemblies where a single grain of dust could cause a malfunction. Every fuse was tested multiple times before shipping. Even then, the initial failure rate was 15%, unacceptable for most manufacturing, but compared to the 0% success rate of previous proximity fuse attempts, it was a miracle. By September 1942, the first production VT fuses were being loaded onto Navy ships. The Navy got priority because ships were isolated. If a fuse malfunctioned and fell into the water, the Germans could not recover it. If a fuse was fired over land and failed to detonate, enemy forces might find it, examine it, learn its secrets. The Navy could test the weapon in combat without risking compromise. The first combat use was carefully planned. January 5th, 1943, the USS Helena, a light cruiser operating in the Solomon Islands, engaged a Japanese air attack. The Japanese were flying low, fast, using terrain to mask their approach. Standard time fuses were nearly useless in such conditions. The Helena's gun crews loaded VT-fused shells into their 5-inch guns and opened fire. The first volley brought down 2 Japanese aircraft. The second volley destroyed 3 more. In less than 3 minutes, 5 enemy planes were destroyed. With fewer than 50 shells, the gun crews were astonished. They had never seen anti-aircraft fire this effective. The Japanese pilots were equally shocked. They had faced American anti-aircraft fire before, learned to evade it, knew its limitations. This was different. This was lethal. The Navy's after-action reports were cautiously enthusiastic. The fuses worked. Reliability was good, roughly 85% detonation rate. Effectiveness was dramatically improved, estimated at 10 to 20 times better than time fuses in similar conditions. But this was one battle, one ship, one set of conditions. The real test would come when the fuses were deployed across the fleet, used in large-scale engagements, subjected to the full chaos of naval warfare. By March 1943, hundreds of Navy ships were equipped with VT fuses. Production had ramped up to 40,000 fuses per month and climbing. The workers at Western Electric still did not know exactly what they were building. They knew it was important, knew it was secret, knew it was saving lives. That was enough. In the Pacific, Japanese pilots began reporting strange experiences: anti-aircraft fire that seemed to anticipate their maneuvers, explosions that tracked their movements, shells that detonated with uncanny accuracy. Japanese intelligence tried to understand what the Americans had developed. They recovered shell fragments from crashed aircraft, examined them for clues. They found nothing obvious, no visible mechanism, no clear explanation for the improved accuracy. The Germans were equally puzzled. Reports from Luftwaffe pilots flying over Allied ships described anti-aircraft fire of unprecedented effectiveness. But the Germans had their own problems. The Eastern Front, the Mediterranean, the defense of the Reich itself. They noted the reports, filed them, and focused on more immediate threats. They would not understand what they were facing until it was far too late. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Merle Tuve had created a weapon, but he had also created a problem. The VT fuse was too effective. Navy commanders loved it, wanted it for every anti-aircraft gun on every ship. Army commanders wanted it for ground-based air defense. The British wanted thousands, tens of thousands, for defense of London and other cities. Demand was exceeding production capacity by a factor of 10. Production in mid-1943 was 40,000 fuses per month. Requirements were 400,000 per month. Western Electric could not expand fast enough. Tuve's team began working with other manufacturers, spreading production across multiple facilities. RCA, Sylvania, Raytheon, companies with electronics expertise, began producing components. Each had to be taught the manufacturing techniques, the quality control standards, the security protocols. The security challenge grew with each new facility. More workers meant more risk of compromise. The compartmentalization became more elaborate. Workers assembling the radio circuits were told they were building experimental radar components. Workers manufacturing the detonators were told they were making standard artillery fuses. Only the final assembly teams knew they were building something unusual, and even they did not understand the complete function. By June 1943, production reached 100,000 fuses per month. The Navy had priority, but the Army was becoming insistent. The 8th Air Force, flying daylight bombing raids over Germany, was suffering terrible losses. Luftwaffe fighters were shooting down bombers at unsustainable rates. If ground-based anti-aircraft defenses in England could be improved, if German fighters could be deterred from following damaged bombers back across the Channel, losses might be reduced. The problem was security. Using VT fuses over England meant using them over land. A shell that failed to detonate, a fuse damaged by flak, any malfunction that caused a fuse to fall intact would give the Germans a complete working example. They could take it apart, analyze it, potentially copy it. The entire advantage would disappear. The decision went to the highest levels. General George Marshall, Army Chief of Staff, consulted with Vannevar Bush, Director of the Office of Scientific Research and Development, who oversaw Tuve's project. Bush consulted with President Roosevelt. The question was simple. Was the immediate tactical advantage worth the long-term strategic risk? Roosevelt made the decision in August 1943. The VT fuse could be used over England, but only under strict conditions, only against German aircraft, never against ground targets, only in areas where recovery of duds would be difficult, only when the tactical situation absolutely required it. The Germans were advanced in electronics, had sophisticated research programs, might be able to reverse engineer a captured fuse. But the immediate need to protect Allied airspace outweighed the long-term risk. The first Army use of VT fuses over England came in December 1943. German fighter attacks on returning bomber formations had become increasingly aggressive. Luftwaffe pilots had learned to time their attacks for the moment when bombers crossed the English coast, damaged, low on ammunition, vulnerable. British anti-aircraft defenses tried to protect them, but standard time fuses were ineffective against fast-moving fighters at varying altitudes. On December 19, 1943, the day Hans Meyer would nearly die over the Channel, the anti-aircraft batteries defending the Dover coast were equipped with VT fuses. The gun crews had received minimal briefing. They were told only that the new fuses would improve accuracy, were not told how or why, and were ordered to fire normally and report results. The first German fighters appeared at 10:45 in the morning, attacking a formation of damaged B-17s. The anti-aircraft batteries opened fire. The first volley produced an unusual pattern. Instead of the typical scattered bursts, explosions clustered tightly around the attacking fighters. The German pilots, experienced veterans, immediately recognized something wrong. This was not normal defensive fire. Meyer, leading his flight, saw his wingman explode. A shell had detonated within 30 feet of the aircraft, close enough for shrapnel to tear through the cockpit and fuel tanks. He pulled into a climb. Standard evasion. An explosion erupted directly ahead of him, forcing him to dive. He rolled left. Another explosion. He reversed right. Another blast. So close, he felt the concussion through his aircraft's frame. In 7 minutes of combat, 14 German fighters were shot down. 7 by the anti-aircraft batteries, 7 by the bombers they had been attacking, fighters so disrupted by the accurate defensive fire that they became easy targets. The German formation broke off, fled back across the Channel. It was the first time in the war that Luftwaffe fighters had been driven away from a target by ground fire alone. The after-action reports from the anti-aircraft batteries were almost giddy. Gun crews reported seeing shells explode directly alongside enemy aircraft. One crew claimed to have watched a German fighter fly directly into a burst, disintegrate, and fall in pieces. Another crew reported destroying an enemy aircraft with a single shell. Unheard-of accuracy. The tactical impact was immediate. German fighters began avoiding areas covered by anti-aircraft fire, even when attacking vulnerable targets. They changed their tactics, staying higher, attacking less aggressively, breaking off earlier. The mere presence of VT-fused anti-aircraft fire altered enemy behavior, made them cautious, reduce their effectiveness. But the Germans were not stupid. They knew something had changed. Luftwaffe intelligence began collecting reports from surviving pilots. The pattern was clear. Allied anti-aircraft fire had suddenly become far more accurate, not gradually, not progressively, but overnight. This suggested a new technology, a new weapon, something the Allies had kept secret and now deployed. The hunt for an intact VT fuse began immediately. German intelligence officers instructed pilots to note where anti-aircraft shells exploded, directed ground units to search for unexploded ordnance, offered bounties for any unusual artillery fuse recovered intact. The British and Americans, aware of this effort, instituted additional security measures. Anti-aircraft units were ordered to police their firing positions after engagements, collect any fragments, destroy anything that might provide information. The race was on. The Allies needed to use the VT fuse aggressively enough to gain tactical advantage while preventing the Germans from learning its secrets. The Germans needed to capture and analyze a fuse before the Allies became so dominant in air defense that the Luftwaffe could no longer operate effectively. The outcome of this race would determine control of the skies over Europe in the final year of the war. By January 1944, VT fuse production reached 250,000 per month. The Navy was using them routinely. The Army was deploying them in England and North Africa. The British were receiving allocations for defense of critical targets. The statistical impact was becoming impossible to hide. Shell expenditure per aircraft destroyed had dropped from 2,500 to under 100. 100 shells per kill. A 25-fold improvement in efficiency. This had strategic implications beyond simple effectiveness. Anti-aircraft batteries required fewer shells to defend a target, meaning fewer supply ships, fewer storage facilities, fewer logistics personnel. Gun crews could engage more targets in less time with higher confidence of success. The psychological impact on enemy pilots was immeasurable. Luftwaffe veterans who had flown hundreds of missions suddenly found their experience and skill irrelevant against a weapon that removed human error from the equation. German engineers, working from fragments and reports, began to understand what they were facing. The shells were not using time fuses. They were using some kind of sensor, likely radio-based, that detected proximity to aircraft. The concept was brilliant. The execution sophisticated. The Germans had considered similar designs before the war, abandoned them as impractical, too complex, too fragile to survive firing. The realization was humbling. The Americans, supposedly inferior in theoretical science, supposedly behind in electronics research, had solved a problem German engineers had deemed impossible. And they had done it in secret, deployed it in quantity, and maintained security so effectively that Germany had no warning, no counter-development, no response. German attempts to reverse engineer captured fuses would fail repeatedly, not because the technology was beyond German capability, but because manufacturing at scale was. The precision required, the quality control, the specialized components, all required an industrial base that Germany in 1944 no longer possessed. Even if they understood the design perfectly, they could not produce it in useful quantities. Tuve's team had created a weapon that was not just effective, but irreproducible. The Germans could analyze it, understand it, even admire the engineering, but they could not copy it. The industrial might require to produce hundreds of thousands of miniature vacuum tubes, micro-generators, precision detonators, all to specifications that required near-perfect quality control, was beyond Germany's capacity in the middle of a losing war. This was the ultimate strategic success, not just a better weapon, but a weapon the enemy could not counter even when they knew exactly how it worked. The VT fuse represented American industrial power in its purest form. Theoretical physics from university laboratories, precision manufacturing from commercial electronics companies, mass production from facilities built specifically for war. It was the integration of science, industry, and logistics on a scale no other nation could match. Hans Meyer survived the war. He was shot down 3 times, wounded twice, finished the conflict in a prison camp. In post-war interviews, he was asked about the experience of facing VT fuses. His answer was simple and bitter. It made us obsolete. We trained for years to be fighter pilots, to read the air, to understand tactics, to outfly and outfight the enemy. Then they invented a machine that didn't care about any of that. It just killed you efficiently, precisely, without caring how skilled you were. That efficiency is what changed air warfare. Before the VT fuse, anti-aircraft defense was an art, a matter of experience, instinct, luck. After the VT fuse, it was mathematics. A shell either got close enough to a target or it didn't. If it did, the fuse detonated. No human decision, no room for error, no way to evade, through skill alone. The individual pilot's ability became irrelevant against a system that removed human limitations from the defense equation. By the spring of 1944, the Luftwaffe had lost air superiority over Western Europe. Multiple factors contributed: Allied numerical superiority, German fuel shortages, the diversion of resources to the Eastern Front. But the VT fuse played a critical role. It made low-altitude attacks suicidal. It made attacks on naval targets nearly impossible. It forced German aircraft higher where they were less effective, or lower where they were vulnerable to other defenses. The statistical record is stark. In the 6 months after VT fuses were deployed over England, Luftwaffe losses in combat with Allied air defenses increased by 73%. Not because Allied gunners became better shots, because the weapon made accuracy automatic. Shell consumption per kill decreased by 96%. Anti-aircraft batteries that had required thousands of shells to defend a target now needed dozens. The impact extended beyond combat statistics. Allied bombers suffered significantly fewer losses on missions after December 1943. German fighter pilots, knowing that approaching certain targets meant flying through VT-fused anti-aircraft fire, became more cautious, broke off attacks earlier, engaged less aggressively. The psychological impact of facing a weapon that seemed to anticipate your movements, that exploded precisely where you were about to be, eroded the confidence even of veteran pilots. Production peaked in 1944 at over 1 million fuses per month. Western Electric alone was producing 20 million vacuum tubes per month, each tested individually, each required to meet specifications so demanding that a single degree of misalignment meant rejection. The manufacturing process employed over 100,000 workers, spread across dozens of facilities, none of whom fully understood what they were building. The cost was enormous. Each VT fuse cost approximately $20 in 1944 currency, roughly equivalent to $300 today, for a single artillery shell. But compared to the cost of losing bombers, losing ships, losing trained pilots and crew, $20 was cheap. The American economy could afford it. The German economy could not match it. This disparity, the ability to spend resources on weapons so expensive that they would have bankrupted Germany to produce in equivalent numbers, was itself a strategic weapon. The VT fuse was not just better technology, it was technology that only a fully mobilized industrial economy could produce at useful scale. Germany could not compete, not because their scientists were less capable, but because their factories were being bombed. Their resources were exhausted. Their infrastructure was collapsing. The invasion of Normandy on June 6, 1944, represented the ultimate test of the VT fuse in combined operations. The Allied invasion fleet, over 5,000 ships, was the most valuable collection of targets the Luftwaffe would ever face. Every German pilot knew that disrupting the landings, even marginally, could alter the course of the war. Every Allied commander knew that the fleet, packed into a narrow channel, loaded with troops and supplies, represented an almost defensible concentration of vulnerability. The Germans attempted to attack. On the night of June 6th and into June 7th, Luftwaffe bombers and fighters flew sortie after sortie against the invasion fleet. They faced a wall of VT-fused anti-aircraft fire unlike anything previously encountered in warfare. Every destroyer, cruiser and battleship in the fleet was equipped with 5-inch guns loaded with proximity fuses. Every shell that came near a German aircraft detonated automatically. The results were catastrophic for the Luftwaffe. In the first 48 hours of the invasion, German aircraft attempted over 300 sorties against the fleet. Fewer than 20 aircraft got close enough to drop bombs or torpedoes. Of those 20, only 3 scored hits, minor damage to support vessels. The cost was 74 German aircraft destroyed, primarily by VT-fused anti-aircraft fire. Commander Paul Schroeder of the German Second Air Fleet wrote in his diary on June 8th, "We cannot approach the ships. The fire is too accurate, too dense. Aircraft are being destroyed before they reach attack range. Pilots are refusing missions, not from cowardice, but from recognition that the missions are suicide. The Americans have created a defensive system we cannot penetrate." The naval commanders had feared that the close concentration of ships, the volume of fire from hundreds of guns, might create interference, might cause VT fuses to detonate prematurely or fail to function. The opposite occurred. The overlapping fields of fire created a defensive zone so lethal that German pilots could not find gaps. Where one ship's fire ended, another's began. The shells formed a continuous barrier of precisely timed explosions. British Admiral Bertram Ramsay, naval commander for the invasion, reported to Churchill on June 9th, "The new fuses have performed beyond all expectations. German air attacks have been almost completely neutralized. Our losses from air attack are negligible. The weapon has proved itself not merely effective, but decisive." The success at Normandy led to expanded deployment. The army, which had been restricted to defensive use over England, was authorized to use VT fuses in ground combat, but with strict limitations. Only against aircraft, never against ground targets where duds might be recovered intact, only in forward areas where Allied forces could police the battlefield afterward. The security remained absolute. No risks could be taken with the technology that had proven so devastatingly effective. But security measures, no matter how stringent, could not prevent the inevitable. On July 14, 1944, German forces overran an American artillery position near Caen. The withdrawal had been hasty, supplies abandoned, including several crates of 5-inch anti-aircraft ammunition. When German intelligence officers examined the crates, they found shells fitted with unfamiliar fuses. The fuses were carefully extracted, packed, and sent to Berlin for analysis. They arrived at the German Army Weapons Office on July 20th. Chief Engineer Dr. Herbert Wagner, one of Germany's leading experts in guided weapons and electronics, was assigned to examine them. Wagner would spend the next month trying to understand what he was looking at. The disassembly was meticulous. Wagner's team used X-rays first, trying to understand the internal structure without destroying the fuse. What they saw astonished them. A complete miniature radio transmitter and receiver, vacuum tubes smaller than anything in German production, a mechanical generator powered by a nose propeller, a detonation circuit of elegant simplicity, all fitted into a package the size of a soup can and designed to survive forces that would destroy any German radio equipment. Wagner's report, dated August 22, 1944, was brutally honest. The Americans have achieved what we deemed impossible. This device represents manufacturing precision and miniaturization beyond our current capability. More significantly, it represents production capacity we cannot match. The fuses are clearly mass-produced, not hand-assembled. The quality control is extraordinary. Every component is made to specifications that would require specialized facilities we do not possess. Continued, even if we could replicate the design, we lack the industrial capacity to produce the miniature vacuum tubes in sufficient quantity. American production of these tubes must number in the millions per month. Our entire vacuum tube production, for all purposes, military and civilian combined, is less than 1 million per month. We're not competing with superior engineering. We are competing with an industrial base that operates at a scale we cannot comprehend. Wagner's report reached Hermann Göring, commander of the Luftwaffe, in early September. Göring's response was characteristic. He refused to believe it. American technology superior to German technology was unthinkable. The report must be exaggerated. The captured fuses must be prototypes, not production models. The apparent sophistication must be deceptive. Göring ordered his own engineers to examine the captured fuses and provide a second opinion. The second opinion confirmed Wagner's analysis in every detail. The fuses were production models manufactured in enormous quantities, representing technology and manufacturing capability that Germany could not match. Göring rejected the second report as well. He would continue to reject evidence of American technological superiority until the end of the war, even as that superiority destroyed the Luftwaffe around him. The truth was that Germany had its own proximity fuse program. It had been initiated in 1939, years before the American program, led by competent engineers with adequate funding. The Germans had explored multiple approaches: acoustic sensors, photoelectric cells, capacitive sensors. They had built working prototypes. Some had even functioned in controlled tests. But the German program had failed at the same point where every other nation's program had failed. The transition from laboratory prototype to combat-ready, mass-producible weapon. The Germans could not make the tubes reliable enough, could not make the generator sturdy enough, could not solve the false trigger problem. By 1942, the program had been abandoned as impractical. Resources were diverted to other projects: guided missiles, jet aircraft, wonder weapons that promised more dramatic results. The Americans had succeeded where Germany failed, not through superior theoretical knowledge, but through different priorities and different methods. Tuve's team had focused obsessively on reliability and manufacturability from the beginning. Every component was designed not just to work, but to be produced by the thousands in factories run by workers with minimal specialized training. Every stage of production included testing, quality control, fail-safes. The German approach had been more elegant, more theoretically sophisticated, but less practical. German engineers designed for perfection, for optimal performance, for showcase demonstrations. American engineers designed for mass production, for rough handling by frontline troops, for operation in the worst possible conditions. The difference in philosophy produced a difference in results. The Germans had beautiful prototypes that didn't work reliably. The Americans had crude-looking devices that worked every time. By autumn 1944, the VT fuse had become standard equipment throughout Allied forces. The Pacific Theater, where naval warfare dominated, used them extensively against Japanese aircraft. The results mirrored European experience. Japanese pilots called them hell shells, explosions that appeared magically around aircraft, impossible to predict or evade. Japanese losses to anti-aircraft fire increased dramatically, forcing tactical changes, higher altitude attacks, less aggressive pursuit of damaged targets. The strategic bombing campaign over Germany benefited enormously. American and British bomber formations, protected by escorts and covered by VT-fused anti-aircraft fire from advancing ground forces, suffered progressively lower losses through late 1944. Luftwaffe interceptors, already outnumbered and short of fuel, found themselves facing defensive fire so accurate that attacking bomber formations became nearly suicidal. General Adolf Galland, commander of German fighter forces, attempted to explain the situation to Hitler in November 1944. German fighter pilots, he reported, were being destroyed at unsustainable rates. Losses to enemy fighters were manageable. Losses to ground fire were catastrophic. The Americans had deployed a weapon that made low-altitude flight over any defended area impossible. German aircraft were being forced higher where they were less effective or being destroyed in numbers that exceeded replacement capacity. Hitler's response was to blame the pilots, to question their courage, to demand more aggressive attacks, regardless of casualties. Galland tried to explain that courage was irrelevant against a weapon that detonated automatically when aircraft came within lethal range. Skill could not overcome it, bravery could not defeat it, tactical genius could not evade it. The mathematics were simple and merciless. Aircraft that flew within range of VT-fused anti-aircraft fire died at predictable rates, regardless of pilot quality. Hitler dismissed Galland shortly afterward, replaced him with a more ideologically reliable commander who promised aggressive action. The aggressive action produced exactly what Galland had predicted: higher losses, no improvement in effectiveness, progressive destruction of the Luftwaffe's remaining experienced pilots. By December 1944, German air power over the Western Front had effectively ceased to exist. The Battle of the Bulge, Germany's last major offensive in the West, launched in December 1944, illustrated the complete shift in air power balance. The Germans achieved initial surprise, broke through American lines, created chaos in the Allied rear areas, but they could not achieve air superiority, even locally, even temporarily. American anti-aircraft batteries, equipped with VT fuses, created defensive zones that German aircraft could not penetrate. On December 23rd, when weather cleared and Allied aircraft could fly, the German offensive collapsed under weight of air attack. German ground forces, designed to operate with air cover, found themselves naked under skies controlled absolutely by the enemy. The VT fuse had not single-handedly won air superiority. Numerical superiority mattered, aircraft quality mattered, pilot training mattered, but it had made German air operations over defended areas effectively impossible, and that tipped an already favorable balance into complete Allied dominance. Production of VT fuses continued to accelerate through early 1945. Monthly production reached 1.5 million fuses by February. The cost had dropped through improved manufacturing to roughly $15 per fuse. Quality had improved. Detonation reliability exceeded 90%. The weapon had become routine, standard equipment, taken for granted by troops who could not remember when anti-aircraft fire had been ineffective. The final accounting of the VT fuse's impact came in March 1945, when Allied intelligence compiled statistics from the previous 15 months of combat. The numbers were extraordinary. German aircraft destroyed by VT-fused anti-aircraft fire, over 4,000 confirmed, likely significantly more unconfirmed. Shell consumption reduction, 96% compared to time fuses. Allied bomber losses, attributable to German air attack, reduced by approximately 60% in defended areas. But raw statistics understated the full impact. The VT fuse had changed German tactical doctrine, forced Luftwaffe aircraft to operate at disadvantage, reduced the effectiveness of experienced pilots, and, most critically, accelerated the destruction of German air power at precisely the moment when Germany needed air superiority most. The weapon had helped create conditions where Allied ground forces could operate with near impunity from air attack, where Allied aircraft could strike German forces without effective opposition, where the final campaigns of the war became increasingly one-sided. Merle Tuve never received public recognition during the war. The VT fuse remained classified, its existence known only to those who used it and those who faced it. Tuve continued to work on other weapons projects, other secret developments, other contributions to the war effort that would remain hidden for decades. He was not seeking glory, not interested in medals or fame. He was a scientist who had been given an impossible problem and had solved it through methodical application of engineering principles and industrial organization. After the war, when the VT fuse was finally declassified, military historians would call it one of the three most important Allied technological developments, alongside radar and the atomic bomb. Some would argue it was more important than either because it was deployed sooner, used in greater quantities, and affected more battles across more theaters. The atomic bomb ended the war, but the VT fuse helped win it. German engineers studying captured fuses after the war expressed a mixture of admiration and frustration. The design was brilliant, but not revolutionary. The components were sophisticated, but not theoretical breakthroughs. What was extraordinary was the execution, the manufacturing, the quality control, the sheer scale of production. One German engineer, formerly with the Luftwaffe technical office, summarized it precisely in a post-war interview. "We could have built one. We probably could have built a dozen, even 100, for testing and evaluation. We could never have built 1,000,000. The Americans didn't just invent a better mousetrap. They invented a better mousetrap and then built 1,000,000 of them to the same specification with the same reliability. That's not science. That's industrial art, and it's something we never mastered." The post-war fate of key figures illustrated the different trajectories of the two sides. Tuve returned to pure scientific research, eventually became director of the Carnegie Institution, contributed to multiple fields of physics and engineering, and died quietly in 1982. His contributions, recognized by specialists but largely unknown to the public. His obituary, in the New York Times, was 3 paragraphs long. Herbert Wagner, the German engineer who analyzed the captured fuses, was recruited by the American military after the war, worked on missile development programs, and contributed to the early American space program. He would later say that his examination of the VT fuse taught him more about American engineering philosophy than any other experience of the war. They were not trying to build the best weapon. They were trying to build the weapon that could be produced in the largest numbers with the highest reliability. That difference in objective defined the outcome. Hans Meyer, the Luftwaffe pilot who survived his encounter with VT fuses in December 1943, spent 30 years after the war flying commercial aircraft. In interviews late in life, he was asked repeatedly about his combat experience, about aerial tactics, about dogfighting techniques. His answers always came back to the same theme. Individual skill mattered only when the fight was between individuals. Once one side deployed weapons that removed human limitations, individual skill became irrelevant. "I was a good pilot," he said in an interview in 1976. "I had excellent training, combat experience, good reflexes, good judgment. Against British and American pilots of equal skill, I had a reasonable chance. Against their VT fuses, I had no chance. The shell doesn't care about my training or experience. It simply calculates distance and explodes when I'm close enough. There's no counter to that, no tactic, no skill. You either avoid the area entirely, or you accept that you'll probably die. We chose to avoid, and that meant we lost the war." The VT fuse remained in American military use for decades after World War II. It was used extensively in Korea, in Vietnam, in countless smaller conflicts. The basic design was refined, miniaturized further, adapted for different weapon systems, but the core principle remained unchanged: a radio proximity sensor that automatically detonated when near a target. The elegance of Tuve's original concept proved enduringly practical. Modern anti-aircraft weapons use far more sophisticated sensors, laser rangefinders, infrared tracking, computer-controlled detonation, but they are descendants of Tuve's invention, refinements of his basic insight, that the way to improve anti-aircraft fire was not to make gunners better shots, but to make the shell smart enough to know when to explode. Remove the human limitation, automate the critical decision, and effectiveness increases by orders of magnitude. The lesson extended beyond weapons technology. The VT fuse demonstrated that in modern industrial warfare, victory went not necessarily to the side with better scientists or better engineers, but to the side that could translate scientific knowledge into mass-produced, reliable, combat-ready weapons, faster and in greater quantities. Theoretical superiority meant nothing without production capacity. Elegant design meant nothing without manufacturing infrastructure. Germany had brilliant scientists, sophisticated research programs, advanced theoretical knowledge. America had factories, quality control systems, and the industrial capacity to turn prototypes into weapons by the million. This was the fundamental asymmetry of World War II, particularly visible in the story of the VT fuse. Germany was fighting an engineers' war, seeking perfect solutions to technical problems. America was fighting an industrial war, seeking good enough solutions that could be produced in overwhelming quantity. The engineer's perfect weapon that arrives in small numbers loses to the industrialist's adequate weapon that arrives in millions. The VT fuse killed over 400 German pilots in its first 6 weeks of operational deployment over England. Roughly from mid-December 1943 through January 1944, 400 pilots who had survived years of combat, who had experience and skill, who represented irreplaceable training and knowledge. They died not because they made mistakes, not because they were outfought, but because they flew within range of a weapon that made their skill irrelevant. The Germans understood this eventually. Wagner's reports, Gallen's warnings, the testimony of surviving pilots all painted the same picture. But understanding came too late. By the time Germany fully grasped what they were facing, they lacked the industrial capacity to respond. They could analyze captured fuses, could understand the design, could even appreciate the engineering. They could not build equivalents in quantities that mattered. This, ultimately, was the story of the proximity fuse, not just a weapon, but a demonstration of industrial philosophy, not just a technical achievement, but a strategic statement. America could afford to spend $20 per artillery shell for a weapon that converted every shell into a potential kill. Germany could not afford even to attempt matching that expenditure. The war was decided not by who had better weapons, but by who could afford to deploy better weapons in sufficient quantity to matter. Tuve understood this from the beginning. His goal was never to build the theoretically optimal proximity fuse. His goal was to build a proximity fuse that could be manufactured by the thousands, used by ordinary soldiers, and maintained under field conditions. His genius lay not in the electronics or the physics, but in the recognition that the perfect weapon that existed only in prototypes was worthless compared to the adequate weapon that existed in millions. The American military learned this lesson thoroughly. Post-war weapons development emphasized reliability, maintainability, and mass production potential alongside performance. The question was never just, is this the best weapon? The question was always, can we build enough of them to matter? This philosophy, born from projects like the VT fuse, would define American military procurement for decades. And the Germans learned the opposite lesson, or rather confirmed what they already believed. Their post-war weapons development, constrained by treaties and restrictions, emphasized quality over quantity, sophisticated systems over simple reliability. The German military tradition valued the perfectly engineered solution, the elegant design, the weapon that was the best, regardless of cost or complexity. This tradition produced remarkable weapons, but also produced weapons that were expensive, difficult to maintain, and available in limited numbers. The contrast was visible in every aspect of military technology through the Cold War and beyond. American weapons were generally adequate, reliable, available in quantity. Soviet weapons, inheriting some German philosophy through captured engineers and documents, emphasized theoretical performance, sometimes at the expense of reliability. The pattern established in World War II, American industrial pragmatism versus Axis engineering perfectionism, continued to shape military technology for generations. The proximity fuse itself continued to evolve. By the 1950s, miniaturization had advanced to where similar sensors could fit in much smaller shells, even mortar rounds. By the 60s, solid-state electronics replaced vacuum tubes, improving reliability further. By the 70s, microprocessors enabled programmable fuses that could distinguish different target types. The evolution continued, each generation smaller, more capable, more reliable, but all descendants of Tuve's original concept. Modern weapons designers study the VT fuse not for its technology, which is primitive by current standards, but for its development process, how Tuve organized the project, how he balanced performance against reliability, how he ensured manufacturability, how he maintained security while coordinating across multiple organizations. The process was as important as the product, perhaps more important, since processes could be applied to future projects while products became obsolete. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.